What's going on, smart people? Today we are finally getting started on the lecture series on Tensor Calculus for Physics. Throughout this whole lecture series, I'm going to be following Tensor Calculus for Physics by Dwight Neuenschwander very closely. Sorry if I butchered that last name. Now for this video and the next video, we're not going to talk about tensors very much, and I'll get into why in just a couple minutes. But for now, we're going to limit the scope of our discussion to scalars and vectors. And by in a couple minutes, I mean right now. So let's construct a tensor real quick, and I'm going to show you why we're not going to start off with them. So here we go. TRS equal to There we go. Here we constructed some tensor T that obeys this transformation law. The reason we're not going to be talking about tensors right off the bat is because most people who start off with them aren't comfortable with describing something or defining an object based off of how it changes. So tensors are usually defined on how they transform, but that's sort of like defining the dollar in terms of the peso. Like, that's not very helpful if the real thing you're uncomfortable with at the moment is the idea of currency. So the goal of this and the next video is to start building up from the bottom the ideas of scalars and vectors, and show that you can take these more familiar concepts and express them in a similar fashion. And what I mean by this is that a lot of people are more familiar with vectors, right? And typically when you think of a vector, you think of something that has a magnitude and a direction. But you can also define a vector in how a vector transforms. So once we build up that, once we show we can take that familiar concept and express it in terms of how it transforms, pretty much after that we're going to jump right into two-index tensors, because I think we'll be ready. So this video we're tackling scalars, vectors, basic properties of them, and maybe express them in a little bit of an unfamiliar way, but still nothing that you won't be able to handle. Next video we'll be talking about vector transformations. And then the following video, we're jumping right into tensors. So first, let's talk about coordinate systems. Now, you might define your location as, 3 feet from the refrigerator, 7 feet from the microwave, and 20 feet from the television. But I might define your location as, 20 feet from the mailbox, 9 feet from the bottom floor, and 8 feet from the couch. The fact that we can impose these coordinates and get the same result, both get where you are, tells us that there has to be a way to convert from one to the other. What I'm describing is a coordinate transformation, and in that definition of the tensor that we had earlier, it was referencing how it changes under a different reference frame. So in defining a tensor, we also get for free essentially a theory of relativity, because it talks about how it transforms under those different reference frames. But at the end of the day, the physics shouldn't care what coordinate system you impose on it. So certain things, let's get some definitions out of the way. If we do a coordinate system transformation, if we transform into a different coordinate system and some quantity doesn't change, that quantity is said to be invariant or scalar under that transformation. In other words, if we have some number, some quantity lambda, and we're saying that that's a scalar, what I'm saying is that if we transform from some coordinate system x, y, z to x prime, y prime, z prime, lambda is equal to lambda prime. That's the definition of a scalar here. This is invariant under this coordinate transformation. Now, vectors are usually defined as something that has magnitude and direction, as I said earlier, but once you agree on a coordinate system that you impose on the vector, you can break it into components, x, y, z, or r, theta, and phi, whatever it is. And because you can break it into these components that contains the information of the vector, that means that that vector now has to obey certain transformation laws to go from one coordinate system to the other. And this is the reason why we're not jumping into tensors right away, because now that we're making the connection that we don't have to just talk about it in terms of magnitude and direction, we can talk about them in terms of how they transform. This is going to make it a much more familiar concept to define quantities in terms of how they transform, and then it'll help us almost seamlessly transition into talking about tensors in a couple videos. Now, some assumptions I'm going to be making before moving on, right? We're not going to be starting from the field axioms of mathematics and building up from there. I'm going to assume you know a little bit of stuff. I'm going to assume that it's not wild to think that you have come across this before. If you have two vectors, A and B, and you want to dot product them together, that's equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And if you do a cross product between two vectors, that's equal to the magnitude of A, magnitude of B, times the sine of the angle between them, times the normal vector. I like to think of dot products as showing how in the same direction two vectors are, right? If you have, really that's only appropriate if one of them is a unit vector, but if the dot product is large, they're probably going in the same direction, or close to the same direction. If the dot product is 0, that means they're orthogonal. So that's how I like to think of those. Cross products, you have two vectors, you do the cross product of those two, and it spits out a vector that is perpendicular to both. And then you could say, well, if you have two vectors, there's two different vectors that could be perpendicular to both. And that's what brings up the anti-symmetry of cross product, meaning A cross B is equal to minus B cross A. So if you have one vector pointing in the x-plane, or in the x-axis, one vector pointing in the y, a vector that's perpendicular to both could be in the positive z-axis or the negative z-axis. That's another way of saying this. One thing that you can also do with vectors is you can take derivatives of them with respect to scalars like time. For example, if you were to have some position vector, r, and you wanted to take the time derivative of the position vector, that's going to be equal to the velocity vector. And one important thing that we sort of take for granted a little bit is that if you have some vector r that's in, say, Cartesian coordinates, and you take the derivative of it with a scalar, the resulting vector is still going to be in the same space. It's still going to be represented in those Cartesian coordinates. And that's not always going to be the case. Sometimes when you do operations on vectors, it gets spit out in a completely different space. So that's something to keep in mind. For the most part, this is what you've been introduced to in like introductory physics classes, but I just wanted to make it a point to say that it's not always going to span the same space. Now, one way to think about velocity vectors is it is a change in a displacement vector with respect to a scalar, but we can sort of invert that a little bit and take the derivative of, say, a scalar with respect to the displacement, and that's what gives us the concept of a gradient. So the gradient, we can define the gradient of some scalar function phi, say dot some vector n. This is what we call the directional derivative. This contains the information that says what direction the function is changing the most. Some examples of scalar functions include things like atmospheric pressure or temperature. So if you were to take the directional derivative of a temperature field, it might be pointing in the direction of where the fireplace is, where the heat source is, where it's most changing. The important thing to note with the gradient operator is that when you take the gradient of some scalar function, what you get is that it spits out a vector. So you have a scalar to start with, you take the gradient of it, and it spits out a vector. I tacked on a minus sign just to show that it's analogous to, say, the force equation, how the force is equal to the minus gradient of the potential. It's pretty common for us to think of the gradient operator as a vector itself, and when we do that, we come up with certain things like dotting it into certain vectors. Like we can take the dot product between the gradient operator and some vector v, and that's what we call the divergence. And likewise, we can do the same thing with a cross product between the two vectors, and we get something that we call the curl. Think of divergence as some water going through a sink, and curl sort of being like a whirlpool effect. We're working without coordinates right now, so we're not going to be calculating any divergences or curls of vector-valued functions, but just want to make sure everyone's on the same page so far. But let's actually change gears a little bit and bring in some coordinate systems now. So we're going to define 3 unit vectors, I, j, and k, and those are going to be defined the usual way. But let's just draw it out just to be safe. Here we have a 3-dimensional axis. Here's some vector k hat. Here is some vector, let's call that j hat, and here is some vector I hat. So this is going to be our z-axis, this is going to be our y-axis, and our x-axis. And some properties of these unit vectors is that, one, they are perpendicular to each other, and they all have unit length. And when you put those two things together, what you get is that they are said to be orthonormal. So since they're orthonormal, what that tells us is that I hat dot I hat equals j hat dot j hat equals k hat dot k hat equals 1. Right, the magnitude, this is just going to be, if they're going in the same direction, remember, so I hat times I hat dot I hat is going to be the same thing as the magnitude of I hat times the magnitude of I hat times the cosine of the angle between them. Since the angle between them is 0, that cosine becomes a 1. Their unit length, which makes it 1 times 1 times 1, all of this equals 1. Now, since all of these are perpendicular to each other, it also follows that I hat dot j hat equals, let's say, I hat dot k hat, which is equal to j hat dot k hat, which equals 0. What I'm going to do now is I'm going to change up some notation. I'm going to let e hat sub 1 equal I hat, e hat sub 2 equal j hat, and e hat sub 3 equal k hat. And that's another big point of this video, is we're going to be calling a lot of the same things, different things throughout there. So I want to make sure everyone's clear on the notation. So anytime you see e hat sub 1, that corresponds to the x hat unit vector. Alright, so then what this tells us is that we can write in a little bit of a shorthand that e hat sub n dot e hat sub m is equal to what we call the kronecker delta. And what this is delta sub nm is equal to 1 if n equals m, and it's 0 if it's not. But what this is really telling us is if n is 1 and m is 1, then we have e sub 1 dot e sub 1, and that's just this thing here. If we have n equal 1 and m equal 3, well then we have I hat dot k hat, and that gives us 0. So that's just a shorthand way of saying the same thing. So we capture these two relationships in one little shorthand equation. Now, one thing to keep in mind about these three vectors is what we call them is it's a complete set of orthonormal basis vectors. I'll define what that is in just a minute, but basically what it tells us is that we can create any vector we want out of a linear combination of these three unit vectors. For example, we can write some position vector r in terms of some x times e sub 1 plus some y times e2 plus some z times e3. One thing that I'm going to do right now is I'm going to change up notation again. Go figure. I'm going to let x with a little 1 superscript be defined as x. X with a 2 superscript is going to be our new y, and so on. 3 is our z. And what we can do now is we can represent this vector a little bit different. We can say that the sum, we can say that r is equal to the sum I equals 1 to 3 of xi e sub I. There we go. Making progress. And just to be clear, you know, if I is 1, then it becomes x1, I1, or e1, and we get this vector, plus 2, which gives us that, plus 3, which gives us this. And we can do this for really any vector. It doesn't just have to be the position vector, which tells us that we can construct some arbitrary vector A that is equal to the sum of I equals 1 to 3 of ai e sub I. Now, I used the word basis vector earlier, and I want to define that now. A set of vectors is said to be called basis vectors. So basis vector, if they span the space and are linearly independent. Okay. Okay, what do I mean by linearly independent? Span of space is pretty straightforward. It takes up all the space. Linear independent, say we have three vectors, u, w, and v. These are said to be linearly independent if this equation here, say alpha u plus beta w plus gamma v equals 0, if this equation here demands that alpha, beta, and gamma equals 0 as well. In other words, vectors are said to be linearly independent if you can't write one of them in terms of the other ones. So for example, I can't express I hat in terms of a linear combination of k hat and j hat. So let's take a look at that one arbitrary vector that we used before. We said A is equal to the sum of I equals 1 to 3 A I E hat sub I. Now I'm going to expand this out a little bit. So this is equal to AX in Cartesian coordinates A superscript X E sub X plus AY EY plus AZ EZ. I'm sort of purposefully switching up using 1's and X's and I's for the purpose of showing you that it doesn't matter, okay? You need to get absolutely fluent with this to where if you call it one thing or another, that's not supposed to be the difficult part for you. This is absolutely the same thing as if I were to say A1 E1 or A1 I hat. It shouldn't matter, okay? But what this tells us is we can actually take dot product. So this is A. And what happens if I want to do A dot E hat sub X? Well, whatever we do to one side, we have to do to the other side. So this becomes A hat, or no, just AX E hat X dot E hat X. And then, well, if we're dotting E sub Y into EX, that's going to be 0. They're orthogonal. Okay, so this term goes to 0, and this term goes to 0. But E hat sub X times E hat sub X is just 1, right, because it's a unit vector. And this tells us that we can define AX equal to a vector dot E sub X. Similarly, we can also define, or it's not defining, we're solving it, AY equal to A dot E sub Y, and AZ equal to A dot EZ. Perfect. Now, pretty soon we're going to be able to summarize all of this stuff in terms of just a completeness relation, because like I said, these form a set of complete orthonormal basis vectors. And we're going to define really what that means in a concise way once we get to Dirac notation, because it'll be much more simple. But for now, we've been working with unit vectors also. But that's a matter of convenience. It's not a matter of principle. So I just want to go over real quick what it means if we were to take the dot product of two basis vectors that aren't unit vectors. So what I mean by that is if we want to take the dot product, I just wrote E vector, not E hat. So when by the way, if I use a hat, that almost always is going to mean unit vector. If it's not a hat, it's not a unit vector. So let's do E hat, E vector sub n dot E vector sub m. That is equal to G sub n m. That might look a little bit familiar to you. This is actually what we call one of the components, or a component to what's called the metric tensor. And we're going to go into that a bit more in detail once we get into expressing vectors in terms of matrices and stuff like that. But just to be clear, when earlier when I wrote delta nm equals 1 if n equals m and 0 else, you could express that in terms of a matrix in three-dimensional space where you essentially just have delta equaling if you're saying n has to equal m, that means you can express this in terms of a diagonal matrix, right? It's 0 if it's off diagonal, and it's 1 if it is on the diagonal. So for this, for the metric, what's going to be changing are these components here. We're going to be dealing with the metric tensor a lot in future videos, but for now I'm just going to do one more thing where we're working with this a little bit, and then we're going to move on. We're going to swap back to using unit vectors for a pretty long time. What I'm going to do now is I'm going to define some vector A again, and this vector is going to be written in terms of some AX, EX, but not as a unit vector now, plus AY, EY, and we're going to say that we have another vector V that is, defined in a similar fashion, BX, BY, BZ. But we can express this vector as a sum, as we had before. So we could say that A is equal to the sum of, say, n equals 1 to 3 of A n E sub n, where now we're using just this not unit vector. And then we can also define our vector B in a similar way. B is equal to the sum. Let's use a different index because it's not necessarily the same. Let's do M equals 1 to 3 M M. And what we're going to do is we're going to find out what is A dot B. Okay, and asking this question, when you ask this question, it's nice to know that we already wrote this out, because we're pretty much going to be doing this dot this. So that's going to be equal to the sum of n equals 1 to 3 A n E vector n dot sum m equals 1 to 3 B m E n. Okay, we can pretty much just pull out this sum, because the sum isn't going to affect this at all, because this doesn't have any dependency on m. So we can rewrite this as the sum n equals 1 to 3, the sum m equals 1 to 3 of A n E sub n dot B m E sub m. Okay, and then this is equal to E sub n dot E sub m A n B m. And that means that this is just equal to the sum, double sum of n equals 1, sum m equals 1, 3, 3. Well, E sub n dot E sub m is just going to be the metric, the component of the metric, so it's just going to be G n m A n B m. So there we have defined what it means to take the dot product of two vectors that are written in terms of not unit vector basis vectors. One thing that we can do now is, since we're working with unit vectors, is we can define a cross product between two vectors, A cross B. And usually you define this in terms of some determinant between I hat, J hat, K hat if we're working in Cartesian coordinates. And we're going to take the components of these vectors, AX, AY, AZ, BX, BY, BZ, And if we want to evaluate this determinant, what I always do if I'm looking at the ith component is I block the column that I is in, and then the row, the upper row, and I evaluate this determinant. So ay times bz minus az times by. So the I component is going to be ay, this is equal to ay bz minus az by, I hat, and it's the minus sign for the next one, and we have j hat, so cover the column that j is on, it's going to be ax bz minus az bx j hat, and the z component, so ax by plus ax by minus ay bx k hat. Okay, this is a little long. What we can do is we can actually talk about specific components of this cross product in a bit of an abstract way. And the way to do that is we're going to use something called the levi-civita symbol. I might have butchered that pronunciation. I'm just going to call it levi-c. And we define this symbol as like an epsilon I j k. And properties of this is it is 1 if it is what's called a cyclic permutation. So that's like saying if ijk, if ijk is say 1, 2, 3, or 2, 3, 1, or 3, 1, 2. You see, if you can almost think of this as like something rotating, if it's always going to the right, then the next one would start over the cycle with a 1, and then the next one will be a 2. Or if you start here on 3, then it'll be 1, 2, and then 3. So that's a cyclic permutation. This symbol is -1 if this is an anticyclic permutation. So if you have something like 3, 2, 1, or let's see, 2, 1, 3, or 1, 3, 2. Okay, and then this is also going to be 0 if you have indices that repeat. So if you have something like 1, 2, 2, etc. And we're going to use this to shorthand an expression for a specific component of this cross product. Okay, so if I want to talk about the ith component of this cross product, I could say, I'm going to write this as A cross B I. And when I write superscript I, that's not saying this is raised to the ith power, it's saying that I'm looking at the ith component. I can write this as the sum, double sum actually, let's say k equals 1 to 3, j equals 1 to 3, of this levi-civita symbol, jk, aj, bk. Okay, let's see if this works out. So let's take a look at the actual ith component. I'm being general with I, it's not the same as I hat, it's just saying, you know, I equals 1, 2, 3. If it's 1, it's x. If it's 2, it's y, and so on. Let's see if this checks out. So here, we're saying that the actual x, the component in the x direction of this cross product, we have a positive aybz. So if we let, say, x, y, z equal 1, 2, 3 respectively, if we're going from y to z, that's a cyclic permutation. So that is going to be a positive. Okay, so that's good. Then we have a z and a y. Well, z and y, that means you're going backwards. That's anticyclic. That's why there's a negative sign here. And then if we go over here, we have x to z. That's also anticyclic because the cycle could go backwards, and then the next one back would be a z, which is why we have a negative sign being distributed here. If we look at zx, that is that's a cyclic permutation, and we have a negative sign, but it's being canceled out here, so it works out. So this is the shorthand for representing a component of the cross product of a vector. Now that we did all that, let's look at some physics stuff. But before we get into the physics, I want to do one more thing where we take a look at the components again of some arbitrary vectors. Let's say that we have 2 dimensions going on here, and we have some vector A. It looks like this. This is the magnitude of A. This is theta, and this is going to be our A sub y, and this is going to be our AX. Let me be consistent. Let me just keep this as a superscript. AY. We said that we can define some component of this, AX, is going to be equal to A dotted into the unit vector I hat. What is that? I hat. And then we also said that we can do AY equal to A dot J hat. And if we're using this as our vector, we can also take a look at the fact that we know that if we take the dot product of two vectors, that's the same thing as the magnitude of both of them multiplied together times the cosine of the angle between them. Okay, so this is the same thing as saying the magnitude of A times the magnitude of I hat times the cosine of theta. Magnitude of I hat is just going to be 1, which tells us that AX is equal to the magnitude of A times the cosine of theta. And if we do a little bit of trig, we can look at what the cosine of theta is. We can see that cos theta is equal to AX over magnitude of A, multiply both sides by the magnitude, and we get magnitude of A cos theta is equal to AX. Cool. So we get agreement there. We can do the same thing with A sub y, only initially it looks a little weird, right? We'll do, because we have AY equal to the magnitude of A times the magnitude of J hat times the cosine. I'm going to use a different angle here. I'm going to call it, let's call it phi. Magnitude of J hat is still going to be 1, so that's equal to the magnitude of A times the cosine of phi. But usually when we look at things like this, we're used to seeing the y components in terms of sines, so this looks a little weird at first. But when we think about it, this is our y-axis and this is our x-axis. And what this is measuring is the angle between A, the angle between where A is pointing, and the y-axis. So it's not looking at this angle, it's looking at this one, which just so happens to be this one. Okay, so when we think of it this way, if we're using this as the angle, it is the cosine of this angle, or the cosine of theta is this over this, which means that we can still use theta here. The conversion to theta tells us that AY can be written as the magnitude of A times the sine of theta. The only difference is that theta and phi are not the same angle. And I'm pointing this out because we're about to do a little physics problem, and I want to make sure that everyone approaches it with care as to, what angles you're calling what. Now, as I've said before, nature doesn't care what coordinate systems you use or what you impose. It's still going to be doing its thing. Okay, what matters is that if you say this equals one thing, and someone else it equals this in a different coordinate system or something, if they truly are describing the same thing, there should be a way to map one onto the other. So what we're going to do now is we're going to do a little physics problem. We're going to solve the notorious block on an inclined plane, and we're going to solve it sort of two different ways. So let's go ahead and draw out what I want to do. What we're going to have is we're going to have another x and y axis. Here's y, here's x, and here is our inclined plane. And then we're going to have a little block on it. Okay, great. And we want to find out what the total force is acting on the block, and we're going to go ahead and let there be some friction here. So everyone knows F equals ma. Hopefully that's not new to anybody. Like going through all this math and physics, and you're like, wait, really? Since when? Okay. F equals ma. It equals the sum of all the forces. The sum of all of the forces is equal to the mass times acceleration. Well, what are the forces acting on this block right now? Well, we have a downward force of gravity, mg. We have a normal force that is always going to be perpendicular to the plane the object is on. Let's call that N. And then we also have a friction force that's trying to keep it from sliding down the ramp. So when we add all this stuff up, all of these forces are going to be this MA. So F equals MA, well that means that mg plus N plus F is equal to MA. And all of these are vectors. Okay? And what this is right now is this isn't even making any assumptions really about the coordinate system that we're using. I drew it on an XY plane, but this doesn't depend on coordinates right here. What we're going to do to actually solve things, to actually understand the system more, is now we're going to impose X and Y components into this, and we're going to solve some stuff. So if I want to find the X and Y components of this force, so this is equal to F, well then that tells us that I can find, say, the X component of this. So the X component of this force is equal to MA dot I hat, right? And that's going to equal I hat times mg. Well, mg is always going to be working in the y direction. So I hat dot something that only depends on j hat, that's going to be 0. Okay, so that's going to be 0. The I hat dot mg is going to be 0. Then we also have a normal force. Okay, so that's going to be... So to find the normal force in the x direction, let's go ahead and project this vector into... Let's just represent this a little bit differently. Well, if we just put this down here in its own little axis, we see that this just looks like another vector. Here's the magnitude of n, and it's going to have some x and y components. And I'm going to call this angle phi, and this is going to be pointing in the positive y direction, so let's just call that n sub y. And this is also going to be pointing in the negative x direction, so I'm just going to call that minus n sub x, or superscript x. So then if we want to find the x component of this, well that tells us we can just take the cosine of phi, and that's going to give us minus nx over the magnitude of n. And then solving for nx, we get nx is equal to minus the magnitude of n times the cosine of phi. One thing to keep in mind though, this phi is not the same as this theta, right? This phi corresponds to the fact that, well, let's look at this real quick. This normal force is pointing in a direction that's perpendicular to the plane it's resting on. So if we take theta to equal 0, it just looks like a block that's resting on a horizontal surface. So that tells us that the normal force, if theta is 0, is just pointing in j hat. So that's 90 degrees. And then we're offsetting that 90 degrees by some angle theta. So that tells us that phi is normally just going to be 90 degrees, because it's normal to the plane, plus that offset that theta is, plus theta. That tells us that we can represent nx is equal to minus the magnitude of n cosine of 90 degrees plus theta. Why am I doing this? Because I don't want to have to deal with two different angles. Alright, and cosine is just sine shifted by 90 degrees. So sine is just cosine shifted by 90 degrees. And here we're explicitly saying shift cosine by 90 degrees. So what we can write this as is nx is equal to minus n magnitude times the sine of theta. Okay, so now we have our first component of the x. We have our first element of the x component of the force. That tells us that this is equal to minus the magnitude of n times the sine of theta. And I think that was worth going through because, again, as I previously showed, the x component isn't always going to have a cosine there. I think a lot of people make that mistake. Okay? So now, what else do we have? We have the friction force. Friction is pointing in the direction, if you could extend this vector, it's pointing in the direction of this force, or sorry, of this inclined plane, if you were to make that a vector. Okay, so the angle between the friction force is still just going to be theta. So that tells us that we can just use the convention, the x component of the friction force is just going to be, so let's call it fx, is just going to be magnitude of f times the cosine of theta. So now we just add that to this. And we have the x component of the force all figured out now. Cool. And now we want to do the same thing with y. Fy, the y component of the force. Actually, before I get started on this, remember that this is equal to m, the x component of the acceleration. So if we divide it by m, what that would tell us is that this whole thing corresponds to the acceleration of the block in the x direction. Cool. Then, so for y, that's equal to ma, there should be a vector there, dot j hat. So this is just in the direction of j hat. So if we do j hat dot mg, that's just going to be, mg. Okay? Because theta is going to be 90 degrees, so that cosine just goes to 1. Then we got the normal force here. So that's going to give us a plus the magnitude of n cosine of theta. That's just following the exact same process we did for here. We shifted it, added the 90 degrees to theta, and there we have it. It's pointing in the positive y direction, so it's going to be a plus. There we go. Whereas when we were doing the x component, this is sort of pointing in the negative x direction. So you can make an argument as to that's why there's a minus sign there. Then we take a look at the f, and we get that this is just going to be plus the magnitude of f times the sine of theta. That equals m-a-y. Hope you can still see that. Cool, so effectively we've just solved this system completely. But one thing to keep in mind that I did not write here, that I just noticed by looking at the direction of this force, see that's why free body diagrams are always so powerful. You can see that the vector is pointing in the negative y direction. So this g is negative. So it's minus mg because the vector itself is pointing in the negative direction. So it's minus mg plus all of this. And then everything else is correct. Moving on. Now what I'm going to do is we're going to solve this a little bit of a different way. And what we're going to do is we're going to rotate our xy axis to some new point such that x prime lies in the direction of this plane. So that's our new coordinate x prime. And we're going to let y prime be perpendicular to that. So here's our y prime. And we're going to solve the exact same system with our coordinates shifted to this rotation. Okay? So now what we're solving is fx prime and fy prime. So in order to do that, let's take a look. Let's draw this in a little bit different of a way, such that now we have the box in plane. Here's our x prime, here's our y prime. And if we draw our force vectors, draw a little free body diagram, now F is pointing like this. This is little f. Normal force is in this direction. This is straight up. And now our mg is pointing a little bit like this. This is our new free body diagram. And now we want to find out what the components of x prime are, the force in the x prime direction. So if we want to do mg, well, let's think about this. So our mg looks like this. And, well, in our old coordinate system, mg was pointing straight down, right? It was pointing at minus 90 degrees. And now we've shifted coordinates such that instead of pointing straight down, it's now pointing like this a little bit. So that tells us that what we can do is I'm going to define this as my new phi, and then this is going to be minus mgy prime, and this is going to be minus mg x prime. And I'm having minuses because it's pointing in the negative direction in all respects. It's negative in the y total and negative in the x prime. That's where these negatives are coming from. And we can solve this pretty much the exact same way. We can see what the cosine of phi is. That's going to be equal to minus mg x prime over the magnitude of mg, which tells us that minus mg cosine of phi is equal to mg in the x prime direction. We're almost done. Now we just need to know what the relationship between phi and theta is. Well, again, so theta, or sorry, mg is pointing in just the strictly j hat direction, minus y. So that tells us it's pointing in minus, it's at least pointing in the minus 90 degree direction. So phi, if it was equal to theta, would be equal to minus 90 degrees. But then it's also going to be turned a little bit, and that little offset is going to be subtracting another amount of degrees, which is going to be theta. So minus theta. Okay? So that's going to give us something that's turning, pointing straight down, and then we're rotating a little bit such that it's pointing this direction, so that's subtracting another amount of theta from it. So that tells us that mg x prime is equal to minus mg magnitude cosine of minus 90 degrees minus theta, which is equal to minus mg cosine of minus, I'm going to factor out that negative sign, 90 degrees plus theta. Cosine is an even function, which means that cosine of the negative angle is equal to cosine of the angle. So this negative goes away. So that tells us that this is equal to minus magnitude mg cosine of 90 degrees plus theta. And as we just did before, we're offsetting cosine by 90 degrees, which tells us we can write this as minus mg sine theta. So there we have the first element of the x prime component of the force. So that gives us a minus mg sine theta. And now, what else do we got? Well, we also have the normal force, but the normal force in this new coordinate system is pointing straight up, which tells us that when we dot our I prime into it, because what we're doing is we're saying that f x prime is equal to ma dot I hat prime, essentially. When we attack the end with this I prime, that just goes to 0, right, because of the perpendicular. And then f, little f, is in the direction of I prime. So that just tells us that this is going to be plus f. Okay, or I guess just to be clear, this is the magnitude of f. This is the magnitude of mg. Okay, similarly, let's move on to f y prime. And now if we consider y prime, if we draw our little vector one more time, so it's pointing in this direction, and we break it into components. If I'm using this kind of notation where I'm measuring this as phi, this is still going to be a minus mg x prime. But for this to work out, we're going to need for this to be positive. Because we're shifting our angle a little bit, we're just, keep in mind that at the end of the day, the gravity has to be pushing down relative to this. So for that to work out, this mg has to be positive, this gy prime has to be positive, and that'll become more clear in a minute. So if we do the same thing, but we'll use sine this time, sine of phi is going to equal mg y prime over the magnitude, mg. And solve for everything, we got magnitude mg sine phi is equal to mg y prime. Okay, and then we're going to invoke the fact that phi is just equal to minus 90 degrees minus theta, and which is just equal to minus 90 degrees plus theta. And we're going to put that into this phi. So that tells us that this is equal to mg sine of minus 90 degrees plus theta. Okay, and sine is an odd function, which means sine of the negative is equal to negative of the sine. So this is equal to minus mg sine of 90 degrees plus theta. And this is just the same thing as cosine of theta. Minus mg cosine of theta. Okay, so far for here, what we have is that this is equal to minus mg cos theta. And that makes sense. That makes sense so far, because if we draw out a free body diagram of the new coordinate system, where it looks like this, F, N, and then mg. If you took away the other forces, it should be moving in the negative direction. Okay, so that makes sense that this needs to be negative, and that's why the y component of that triangle had to be positive. Okay, so what else do we have? What's the remaining components that we have to solve for? Let's see, well, F is in the x prime direction, remember, y prime. Okay, so if we're looking at the y component of f, that's going to be 0 because I hat prime dot f is going to be perpendicular, it's going to be 0. And then if we look at n is a positive value, it's in the same direction as j prime hat, so the angle between y prime and n is going to be 0, which tells us that this is going to be the magnitude of n. So here we have our new solution to the system. And then I just added the system that we just solved in terms of x and y that we did previously. And one thing to notice is that we started with something that was independent of coordinates, and then we imposed different coordinates that made certain simplifications, and we got different results. Okay, but this is supposed to describe the same physics, the same thing that's going on, which means that these two things have to be equivalent. And if they're equivalent, there has to be a way to map our x and y prime to our x and y. There has to be a way to transform from one to the other if these truly do describe the same thing. And how to go about doing that is going to be the topic of the next video. I really hope you guys enjoyed this first video in a long series of videos to come. Let me know in the comment section if anything I did here was unclear, and I'll see you guys there.